So I hope everyone can hear me well. Hello everyone, my name is Alexandru and this is Stefano, my colleague from ENTSOE, and today we will be talking to you about the ERAA and the scenario building TYNDP models, which are two of the flagship products that ENTSOE does on a regular basis, both of them heavily involved in Plexus. Since this is quite a short time span, we will only be having time to give a couple of introductory notes on both models. But we are eager to talk to you about any questions you might have later here or outside in the corridor. So let's start with the ERAA. The European Resource Adequacy Assessment is a legal mandate from the European Commission, which is done on a yearly basis from ENTSOE to assess the resource adequacy of Europe, let's say. And this year is the third iteration that was finished after ERA 2021 and 22 and 23. It is also the first year when it has gotten approved by Acer. And it was a long journey to get it approved. To give you a quick introduction on how the process looks like, at the beginning of the year, we have a data collection where TSO submit their data and national estimates. We complement that with central assumptions on our side on different unit efficiencies, on fuels and fuel types. Then we run an economic viability assessment to assess the model, the commissioning and decommissioning at European level in the next 10 years. And with this central reference scenario, we run the full adequacy assessment to get our adequacy metrics. For today, I will only be focusing on the first part, the first model, which is the economic viability assessment. And the objective of this model is to bring insights into the impact of uncertainties on market-based capacity. So we're talking about the energy-only market here. And we want to answer how likely we are to have investment, retirement, mothballing, and lifetime extension of units at a European level. To do this, we use Plexus to run a pan-European investment model using a multi-year stochastic overall cost minimization approach. What does that actually mean? So multi-year is because we have a time horizon of 9 years, this for ERA 2023, 10 years for 24, with 4 target years from start to finish. Target years meaning that we basically receive data for these years specifically, and we have some data like demand or inflows, solar data, which is only available for these target years, or we only input it for these target years. And then we have gap years in between, which are not specifically modeled in both the EVA or the adequacy, but which are considered in terms of cost, revenue scaling, and for cash flows. On top of that, we expand our view of the future with the perpetuity option, so-called. You might have heard about it in the advanced training. But basically, the aim is to avoid an end-of-world scenario, especially because we run an investment model. So we want to have the cash flows running into the future. Then we said it's a stochastic model. It's a stochastic model because we have multiple weather scenarios, specifically 3 of them, which are applied to all target years. And this is to represent the uncertainty of the weather in our investment decisions. And the weather scenarios impact both the PV, wind, hydro availability, as well as the total demand that we input into the model. And each of these weather scenarios are also attached to a certain weight to make it as comparable as possible to the expanded weather scenarios that we have in the adequacy model. Between 2022 and 2023, there have been quite a few innovations in how the EVA is run. My colleague Yasser Tohidi was last year presenting in Barcelona how we were trying to address some issues in the EVA. But now that we have a full final report, we can say that indeed, especially for Plexus, last year we were running a limited horizon where the EVA would see initially one step of 3 years and then multiple steps of 2 years. And of course, if you think of an investment model, this is not ideal because you have a limited foresight and you cannot see which units are coming in 2030. You might invest in 2029, but then that capacity is coming in 2030. For this year's EVA, we managed to run it in one step for the full horizon by using the sample chronology. So you see here in 2022, we had a fitted chronology. Now we have it sampled, where we skip these gap years. We don't need to do any more interpolation, which also saves a lot of trouble. And we also were able to run it on full granularity, so not 18 blocks per day. And on top of that, as mentioned earlier, we include this perpetuity function to continue the cash flows of the last year into the future, and potentially also have some investment in 2033, which would not be there if the world would have ended then. To conclude, there are throughout the years now you can see how our modeling approach has changed and has evolved. So we started in 2021 having a deterministic economic viability assessment for the climatic years. Then in 2022, as I showed, it was already a stochastic model, so we already had the 3 climatic years. However, it was not done with full horizon in mind. And this year, due to a number of changes that we worked with, also with Energy Exemplar, and a number of improvements in Plexus, as well as on our side on the quality of the data, we were able to run it single step, multi-year, and with perpetuity. And for this year, in 2024, we are still working hard to improve this economic viability assessment by either potentially increasing the number of weather scenarios that we have in the model, by including flow-based domains in the model, which for now are only included in the adequacy assessment, and in general, by trying to represent better the granularity and the horizon that we are working with. With this, I will finish my part of the presentation, and we can then take questions later on this. And I give it to Stefano.
Thank you, Alexandru. Can you hear me? Okay, good. So now let's see another assessment that is developed by ENTSOE. Actually, it's developed jointly together with our ENTSOE friends. And the aim of these assessments is to build scenarios which are in line with European targets regarding emissions. This cycle for TYNDP 2024, we have 3 main scenarios. One is called National Trends, which is a bottom-up scenarios that come from TSO's data, basically from NECP, so National Energy and Climate Plans, and they are supposed to be in line with Fit for 55 or REPowerEU target in 2030. We have this scenario also for 2040. And then the other 2 scenarios, which are called deviation scenarios, that are the scenarios made using the capacity expansion model in Plexus. Starting from NT 2030, we expand these 2 scenarios, which are called distributed energy and global ambition, with 2 different pathways following different storylines in order to better capture the uncertainty that we have for energy systems, especially in 2050. Respect to the previous cycle, we have 5 main innovations, so respect to TYNDP 2022 scenario building. The first one is the hydrogen modeling in Plexus, that this time has 2 hydrogen zones, and also synthetic fuel production is included, and the direct conversion between hydrogen and power through hydrogen CCGT. The EV modeling, that for EV passenger cars from this cycle is explicitly modeled into Plexus. The offshore modeling is another innovation. This time, we don't have only offshore wind power radial connected to their market zone, but we introduce offshore hubs. Heat modeling, like EVs, hybrid heat pumps are explicitly modeled in Plexos. What are hybrid heat pumps? Are electric heat pumps coupled with a boiler that can use hydrogen or methane. And the model decides what to use for covering that part of the heating demand for prosumers, depending on commodity prices, but also on the temperature. And last but not least, the expansion modeling approach that we used for this cycle that enabled us to increase the granularity of the simulation in order to model better the battery respect to the previous cycle. Here, a general overview of what we find in Plexos. So this is the model. As you can see, it's divided in two big parts. The electricity sector, which is in yellow on your right, which has two main nodes, the electricity market node and the prosumer nodes with their respective demand, native demand. And as I mentioned before, from this year, we have also two EV nodes, one for the street and another one for prosumer. And on your left, you can see the hydrogen model, with two zones. Zone 1 is more focused on the industrial part of the demand of hydrogen, while Zone 2 is the future hydrogen market, and that's why it's there that is included the demand for synthetic fuel production. On the bottom, you can see the offshore wind hub that the model can decide to build for producing electricity or hydrogen or both, and that's why it's linked both to the electricity and hydrogen market. Dedicated RES are renewables that can be built for the model only for producing hydrogen, while on the top, shared RES are renewables that the model can decide to build only for hydrogen, building also the electrolyzers, or only for electricity, building the electricity infrastructure, or for both. What are the expansion candidates for this cycle? We have all the renewables, so solar PV utility that is in e-market node, together with wind onshore and utility batteries, while in the prosumer node for electricity, we have solar PV rooftop and prosumer batteries. While for hydrogen, there is the possibility to install the hydrogen storages like salt caverns. And of course, also dedicated RES, shared RES, and offshore wind hubs are candidates. Here, let's see more in detail what is the innovation with the offshore modeling. So basically, we split the offshore modeling into two categories, depending on the distance from the shore. So till 22 kilometers, all the wind power that is there is excluded from the model because it has a big impact on human activities. Between 22 kilometers and 50 kilometers, all the wind power that is there is radial connected to their market zone, while from 50 kilometers from the shore, it's in the offshore hubs. And of course, there is also the possibility, we can have also different configuration for offshore hubs depending on the water depth and the technology that is used. And the investment costs, of course, change with the configuration. This is the offshore hub, so as I mentioned before, there is the possibility to build an offshore electrolyzers on site for producing directly hydrogen there and then transporting hydrogen from the hub to the shore through pipeline, or producing electricity and transporting electricity through electricity cable. Let's say this is a good trade-off between accuracy and complexity, this kind of modeling, and we gave the model a good level of freedom in order to decide the most efficient path for wind power infrastructure. Last but not least, the expansion modeling approach that we used in TYNDP 2022 scenarios. We ran 25 years from 2025 to 2050 with 8 sub-time horizons of 5 years and 2 years overlap. But the problem with this approach was that the simulation time was very high, and mostly important, the granularity was too low. We had fitted chronology with 3 blocks per month, and we didn't see any expansion for batteries because we couldn't model well the battery behavior, and that's why we decided to switch approach. Now we have 5 years run only, 3 blocks per day, which are defined ex ante in that way in order to better capture the solar PV generation curve. And basically what is changed is that in Plexus you see only 5 years. That should be equivalent to the target years that we want to model. So 2035, 2040, 2045, and 2050. They have to be exactly the same regarding decisions. And what is the parameter that Plexus uses for economic decision is the net present value. So we have to assume that net present value for the 5 years model is exactly the same of the net present value that we would have in a 20 years model in the target years. For doing that, we assume that the discount rate of the 5 years model is equal to 1 plus the discount rate of the 20 years model raised to the power of 5 minus 1. Of course, this is a simplification, and there is the assumption that all the investments are made exactly in the target year and nothing happens between the target years. But as I mentioned before, this enables us to model properly the battery behavior. So that's all, and I invite you to, if you're interested, of course, to have a look at scenario building website, because yesterday we published all the scenario package, so you can see results, main figures, the report, and also the methodology. And yeah, feel free to ask questions to me regarding scenario or to Alexandru regarding ERAA if you have. Thank you for your attention.
All right, do we have any questions out there? All right, we got a question here. Anybody running mics? Here we go. Yeah, I got it. Here you go.
Yes, thank you for your presentation. I had a few questions. First of all, I wanted to ask you, you have spoken about prosumers and electric vehicles. I wanted just to ask you if you can give a quick insight on how you model it. Since I'm familiar with static demand curves, I just wanted to ask you a little bit about this.
Okay, I think I should have a backup slide with the tool chain so you can understand how complicated it is. So this is scenario tool chain, and basically the demand calculation both for market and prosumer regarding electricity is made, the main figures comes from the energy transition model that is an open source model by Quintel that you can find on the website, and we basically took the demand from there, assuming many variables with the help of TSOs, like a number of heat pumps, number of electric vehicles, and so on. And then we take that yearly figures into the demand forecasting tool on the right, that is an ENTSOE tool, which converts the yearly demand into hourly profiles, and then this is the input for Plexus.
Any other questions? All right.
Thank you. I am from the Czech Power Utility, Pavel Rezabek. A simple question, do you use flow-based modeling or NTCs?
In the Economic Viability Assessment model, I assume I can reply this for ERA. For the Economic Viability Assessment model of last year, we used only the ENTSOE model because it was too computationally complex at that time to use flow-based. But in the adequacy model, so the adequacy metrics come from a full flow-based model with curtailment sharing integrated. So for the investment model, only ENTSOE. This year, we are working on implementing flow-based. But on the adequacy model, let's say, flow-based was already integrated.
In scenarios, no. We model only NTCs because, I mean, the purpose is different, and for building scenarios, we have so many uncertainties, especially in 2050. I mean, the pros of modeling flow-based probably are less than the cons of increasing the complexity of the model.
Dražen Balić, Energy Institute, Hrvoje Požar. I have in fact two questions regarding the resource adequacy. So today you presented the EVA analysis, which is done with Plexus. And my question, the resource adequacy, did you done it with Plexus as well or with some other tool? And the second question, you mentioned in these scenarios you used 2003, I think 1995, and the third year, which is in fact climatic years. How you decided to use just these 3 years for EVA? Does these years represents the, from probabilistic point of view, the results from resource adequacy, or you have some other criteria for selecting these years? Thanks.
So on your first question, all of the results that are published for ERA 2023 are based on Plexus. So both the EVA and the adequacy model were run on Plexus. However, we are always trying to benchmark our results with multiple tools. And this year as well, we are continuing to explore parallel streams with different tools apart from Plexus as well. And on your second question, the 3 weather scenarios that were selected indeed were done through a clustering approach based on the full set of 35 climatic years that is present in the adequacy model. And I mean, if any of you has any background in statistics, I think it's quite easy to understand that selecting 3 out of 35 is quite hard to then have it be a perfect representation of a pan-European setting. So we tried our best to also calibrate these 3 years that were selected with a set of weights. And we actually have 2 different set of weights that we published. So we have also a sensitivity on that to understand a bit what is the impact of having a different representation of these 3 weather scenarios in the decisions that our EVA model takes. But yes, we have a clustering approach in order to select them as close as possible to the full set.
All right, do we have any more questions? We have time for one more. Yeah. I know most everybody wants questions for ENTSOE, so.
Good work, guys. Nenad Jovanovic from Holland. You have shown in one of the slides that you also have a dedicated renewables to use only for production of hydrogen. So a question, have you got any results that there are some dedicated RES for hydrogen? And if you did got some results, have you maybe taken into account to use batteries for curtailed energy in that case that can be stored and then used again for the electrolyzer? Thanks.
Thank you for the interesting question. Yes, there are dedicated RES that are built from the model. I don't remember exactly the numbers, but I invite you to look at the report for the insights. But regarding overgeneration, there is overgeneration in the model and is handled using batteries, using storages, using flexibility overall. And regarding for dedicated RES, no, dedicated RES are only solar PV utility or wind onshore power plant that produce electricity for hydrogen.
All right. Well, thank you guys. Really appreciate it.